Similarly, in this STM8 lecture, I will definitely create a repository on GitHub, just like I did in my other lectures, categorizing each lecture by tags. You can go in and check it out. Last time, I used a template, but instead of using that template in the lecture, I created a separate repository with it. I will provide a link to this in the description below the video. Now, let me hide the terminal for a moment. As you can see, I have the code configured in the main section. In this session, we will be working on controlling GPIO digital signals. But before that, at the top, you will see the clock settings. The first part here is related to configuring the CPU prescaler. Next, this is the part where we set the internal clock and the prescaler. By setting this up, you can make the clock run at 16 MHz. So I always keep this setting and use it. Next, we will set up the digital output. And for this configuration, 2 pieces of information are needed. Now, regarding the port information, and pin information, as well as how to configure them when inputting, in this particular session, we will set it up specifically for output only. We need to decide thoroughly whether to set it as input or output, and whether to configure it carefully as open drain or push-pull. Additionally, we can set the speed to high or low, or whether it should be fast. However, this configuration is not arbitrary. It is based on the datasheet, which I have placed in the Documents folder for your reference. If you look at page 11, you will find the pin description. It states that OEB is slow with a maximum of 2 mHz, while fast can go up to 10 mHz. Pins 53 and 54 can be set programmatically for fast or slow, but the default is slow for 53 and fast for 54. Furthermore, the datasheet specifies whether open drain is possible or if it should be set as push-pull. This is crucial for understanding the configuration process and setup of the pins and ports appropriately and correctly to ensure proper functionality and performance of the system as a whole, and to avoid any potential issues or malfunctions that may arise from incorrect settings or configurations. So, actually, looking at the pin map for the STM8S103F3, this is the pin map. And the pin I am using from this side is pin 5 of port B. In the case of port B, it's PPB5. So if you look at the output side here, as you can see, the speed is at the present moment 5, 1, which means it's slow. And therefore, it is operating at a reduced pace. So I made a mistake. Here, it should be slow, not fast. Then, if you come back down and look here, the push-pull is not working. Port B can be open drain, but from the main side. The push-pull configuration is also incorrect. So, to input correctly, you need to set the GPIO mode to output, open drain, and initially set it to low, and then configure it to slow, like this. You have the GPIO pins you want to use, right? Check whether the GPIO pin is 5.1, 5.2, or 5.3, and confirm which option is available between open drain and push-pull. After that, you can set the output pin configuration by inserting this macro variable here. I have done it this way, and then I used the basic light reverse to toggle. If you go into the commands here, there are 4 main commands related to output. There are light mode, high, low, and reverse. In the case of light, such as those who are familiar with assembly-based control, will likely recognize that by using GPIO and ODR, you can directly manipulate the register to quickly activate multiple pins. Using light high, light low, and light reverse, let's divide the blinking function into three methods: void, hoggle, by, and write.
Next, as you can clearly observe right here in front of us, we have the port coming in first. Indeed, the port. This is port B, it's port B, and this is 5. Assuming there are a total of 8 cases for each port, represented as 0, 1, 2, 3, 4, 5, 6, 7. We are currently using pin B5. In this context, each number from 0 to 7 represents a unique case or scenario for the port, allowing us to address specific configurations. So, we perform a shift 1, 5 to right, which involves shifting the bits in a particular manner to achieve the desired output. This step is crucial as it ensures that the correct data is written to the port. Since there are no other pins available for use in this particular setup, we set them to 0, effectively disabling them to prevent any unintended interference. Then we set the delay and duration to 1000, which means we are configuring the system to wait for a specific period before executing the next operation, ensuring that all processes are synchronized. We will then try to flash it, which involves sending a signal to the port to execute the programmed instruction. As you can see, it blinks the same way, indicating that the operation was successful and the port is responding as expected, just like we saw earlier. You only need to input the port name, and it allows you to set all the pins in that port based on 1 byte. This simplifies the process significantly as it reduces the complexity involved in configuring each pin individually. Then we move on to the general method, which encompasses a broader range of operations and provides a more comprehensive approach to port configuration. This method is particularly useful when dealing with multiple ports or more complex systems, as it offers greater flexibility and control over the configuration process. For reference, in electronic circuits, the behavior of components like LEDs can be controlled by manipulating the voltage levels on specific pins of a microcontroller. In this particular case, we are focusing on pin B5. When pin B5 is configured to a low state, which means it is connected to the ground or 0 voltage, the LED is activated and emits light. Conversely, when pin B5 is set to a high state, meaning it is connected to a positive voltage, the LED remains illuminated. This might seem counterintuitive, as one might expect the LED to turn off when the pin is high, but in this setup, the LED is designed to stay on regardless of the pin's state. To introduce a change in this behavior, I will modify the signal sent to pin B5 to a high pulse. A high pulse is a brief period during which the pin is set to a high state before returning to low. This alteration will cause the LED to blink, as it will only be on during the... So in the case of something like write high or write low, you need to input both the port information and the pin information. To control the GPIO pins on your microcontroller, you can use a series of commands that allow you to manipulate the state of the LED connected to these pins. The first command, light high, is used to activate or turn on the specific port pin associated with the LED. This action sends a signal to the microcontroller, instructing it to supply power to the LED, thereby illuminating it. Conversely, when you want to turn off the LED, you use the light low command. This command effectively cuts off the power supply to the LED, causing it to turn off. Additionally, there is a command called light reverse, which is particularly useful for situations where the LED has been in a steady state for an extended period. This command toggles the current state of the LED, meaning if the LED is on, it will turn off, and if it is off, it will turn on. By using these commands, light high, light low, and light reverse, you can achieve precise control over the LEDs. In this session, I explained how to control digital outputs using GPIO. In the next session, I will explain how to control digital inputs with this GPIO. Well then, I will see you next time.